Okay, and now we'll start recording on the frequency response part. Okay, yeah, so on YouTube, there are actually the older recordings. Yeah, I didn't use the other recording tool either. so we missed the beginning. Sorry. Not sorry for you, but sorry for the other guys. All right, so frequency response. About that, and then now I probably better annotate again. So if we have a e to j omega point here, and basically if you go around full the way, so here we have basically minus omega. What is the physical meaning of negative frequency? It's the same frequency except the phase is opposite. Yeah, negative. Okay, so the same way as on the analog systems, you have the imaginary axis is for the frequencies. There you have the upper half. The positive side is actually the mirror image of the negative side, or vice versa. In here, the symmetry is actually on the both sides of the real axis. So yeah, so practically negative and positive angular rates mean the same physical frequency, just the opposite phase. Okay, let's go back here. So for the frequency response, it is enough to draw the frequency response from 0 to sampling rate divided by 2, which is the Nyquist rate. Okay, and then we have also this phase response. So magnitude response and phase response. Okay, amplitude response and zero pole plot. This might actually give you some ideas how to, okay, I see, sorry, this is supposed to be here. For some reason, it's putting this formula in 2 lines. So if you take the absolute value of the product form of the transfer function, remember that it had these roots, each polynomial in complex plane, nth degree polynomial have exactly n roots, which are the numerator polynomials roots are zeros of the system, and denominator polynomial special points are the poles of the system, zeros and poles. If we take and calculate this one, we can quite fast see, okay, here we have, yeah, absolute value of that total gain of the system. But then we have actually taking this absolute value inside of the product. That capital pi here is the product, marking the product again. And here we have the e to j omega minus zk. Ah, wow, which is distance between a point on the unit circle and 0, or here in this case pole. So how to graphically estimate the amplitude response is you actually will calculate these distances, measure the distances and calculate this the formula. And here we have these 3 distances to, wow, That's supposed to be somewhere else. And colors are different. I changed those yesterday, and I'm sure that they were correct, but now now these colors are opposite. So this blue should be actually underlining here. That red should be underlining here. Sorry, I need to make this actually with some other tool, I think. Okay, but anyways, so distance to origo on a point which is on the unit circles is always 1. So finite impulse response system such as this running average filter, the denominator will become 1. The numerator distances will be this distance times this distance times this distance. That's the numerator part. And actually it ends up at the the faraway point, which is right here. That would be where the system gives unity gain. So we have this distance plus that distance plus that distance, and then we have this multiplier here that will actually give exactly the unity gain at that point. Okay, lots of things happening here. However, so that is the maximum point on the amplitude response because it's the longest distance to any of the poles. While actually when we are at the top of this unit or at the same angle as the zero, the system response here goes to 0. The amplitude response goes to 0. And same here. So let's go and take a look at here. Okay, so we had the angular frequency of pi over 2, which is this one, 11,025 hertz. System response goes to 0. Okay, it doesn't show it. It's actually way below here, but it's of course numerical calculation. It doesn't show any infinity values. And another 0 point is right there at 22.05 kilohertz. And these are matching exactly the angles of the where the zeros are located on unit circle. Okay, here I have a small animation of yeah. So this is calculating the amplitude response on linear scale. See, so you know that you never use linear scale, but for this this effect, I have drawn it that way. So we start on this angle and moving this point on unit circle and calculating this product. It gives you nice smooth values for the amplitude response. Okay. Back to the big picture again. Oh, I don't understand those colors now. Okay. Amplitude response. More. So yeah. So local minimas on the angles of zeros. Of course, since this amplitude response gets the minimum values when the numerator goes to minimum. since basically you cannot take these poles on the other side of the unit circle. That would mean the system goes unstable. So you cannot minimize this by adjusting the poles. You can minimize only by setting a 0 on the unit circle or nearby. That's how you get the distance short at some point. Okay. Likewise, when you want to have a maximum, when you want to have local gain at some certain frequency range, then you can actually put a pole near the unit circle, and that results in a gain of signals on that. So basically, if I would take this pole close to the unit circle here, it would definitely give a short distance at that point. Or here you take the pole and move it close. That will give you more gain at that angle. Okay, but seeing is believing. I have a couple of animations here. Okay, that's I'm moving the zeros on the unit circle. Then I start moving the pole closer to the unit circle, and as you can see, the gain at that angle increases. Q factor is also getting better, and here I have to split the those poles because you need a complex conjugate pair, same way as in analog systems. Okay, now it actually started that one again. So first moving the zeros, and now we are moving the pole again, increasing the magnitude response. Then I split the poles and start moving this gain on different angles. Okay, and Q factor keeps being about constant. Okay, another thing. This is the poles are usually used to either adjust the gain on certain frequency to get high Q factor, or as in here, it flattens the magnitude response on passband. So this basically resembles a bit of the analog Butterworth filter, which is used quite often in analog on the audio electronics, since it has a flat passband, doesn't distort the frequencies so much. But on the other hand, this cannot be implemented in reality, this kind of behavior really effectively on analog systems, since it has the zero response at some certain frequency. So think this as a low pass filter for a system which happen to have some line noise or something like that. So you use these poles to adjust a flat passband frequency, passband response, but then you also can adjust the location of zero to get rid of one frequency component. Okay, lots of things happening again. That was about the phase the amplitude response mostly on the frequency response, the one part. Let's not forget phase response. Sometimes it does not have much meaning, but on the other hand, it could be very critical. As in, say, data transmission, it's quite crucial that you will keep the phase response as linear as possible. On analog systems, there's the Bessel filter, which is optimized for the nearly linear phase response on passband. On digital systems, you can have fully linear phase response on passband. And actually on digital system, you can also have zero phase response, meaning that, well, the signal does not delay on the system at all. Okay, of course, this cannot happen in real world, but remember, we can also do lots of post-processing in digital world. Analog world, it's quite hard to actually save the signal in analog means and process it twice. Well, actually, it can be done. Just run it backwards, filter it with the same. Yeah, could be done. I don't know why, but okay. So zero phase response, no delay of the system. Signal means some post-processing tools. Linear phase response means that the phase response is linearly proportional to the phase angle. So it's just a constant k times the angle. Okay, and nonlinear phase response is anything else. Another idea on term group delay. This should also have been actually a part of this analog signals courses what you may have had. So group delay measures the signal delay time. And simply speaking, it's just the derivative, angle derivative of the phase angle. So for linear phase response system, that k gives the delay time. And the linear phase response preserves the shape of the signal because the time delay of the signal does not depend on the frequency anymore, but a say 50 Hertz signal has exactly the same time delay as 2 kilohertz signal, same delay as 20 kilohertz signal. Whatever the frequency is, the time delay is the same. So if you think of a data transmission where you are using actually multiple bands, multiple frequency bands, so multiple frequencies to carry the information, you probably want all the frequency components to pass the system the same time. So in that kind of system, it's crucial to have a as linear phase response as possible. Okay, likewise, zero phase response systems has zero time delay. Yeah, so on post-processing world, you can do it. Nonlinear phase response systems will skew the signal, and you can see it, and you can remember it from the this AC circuits laboratories. Since I have a picture coming. So topmost is the input signal for a digital system. The second one, system has a linear phase response. And linear phase response actually, first of all, there is a considerable time delay. So it's about on here, so it starts at 21, so that's about 30 something would be the starting point, or the, well, depends how you define it. So practically this should have a 10-point time delay. Well, actually 12 points. I think this was second order system. So linear phase response of a system, it looks like that. It has symmetry. So practically these paths which are going either the overshoot or undershoot, these are also mirror image of each other. So it has exactly the same amount of undershoot than overshoot. If you have a nonlinear phase response, this resembles a bit like the analog systems, since in analog systems you don't usually have this preamble kind of the undershoot before the signal starts rising. Here we have the signal starts rising, and then it overshoots and then settles here. And when it goes down, it starts again going down and undershoots and the oscillates a little bit and decays out. Okay. So this is how natural systems usually behave. This symmetry is different. It's mirror symmetry, but it's mirror on the values. Yeah. And here in linear phase response, we have mirror symmetry in time also. Okay. Zero phase response systems has no time delay. This filtered signal is on the same time as the original input signal. Okay, and it has nice the symmetry also, time and values mirror images. Okay, wow, that was the responses part. Let me go really quickly through this one again. So we have impulse response, which is defined actually just as the what is the output for a signal, for a delta signal. Okay, nothing more than that. But it defines if the system is characterized as finite impulse response system or infinite impulse response system, FIR or IIR system. And here's the feedback. You must have feedback in order to have an IIR system, but if a system has a feedback loop, it still can be FIR, like in recursively calculated running average. Transfer function and impulse response, they are practically the same thing. So the transfer function is simply Z transform of impulse response. Zeros and poles. FIR system have all poles at origin, or actually it can have a zero and pole at the same location anywhere. So this would be the recursively calculated 4-point running average filter, and this is the normal running average filter, which, well, it's the same system. So of course, it's the both of these are then the FIR systems. Meanwhile, the infinite impulse response system have at least one pole outside of the origo, so not zero, somewhere in here. And these must be, well, complex conjugate pairs. Step response, which is system output for unit step input. Okay. So basically you can compare a digital domain system with the analog domain system by just measuring the step response of both of them. Arbitrary signal response. Yes, it can be calculated from the difference equation. Just remembering that it's not the most efficient way. Then frequency response is actually the absolute value of, sorry, frequency response is the transfer function evaluated on the unit circle of the complex plane. So e to j omega is actually a point on the unit circle, omega, where the omega is the complex angle related to physical frequency. And amplitude response is simply this absolute value of magnitude response. Magnitude response is absolute value of transfer function frequency response. Oh no, this I'm getting. It seems that I'm getting tired. Too many things. 1 hour already here. Sorry about that. It's Friday. TGIF. So phase response is simply the phase part of the frequency response. Okay. And that's the 4-point running average filter example. And here's the formula how to calculate the omega for any given frequency and the physical frequency when you have the sampling rate known. And there is a graphical representation of zero pole plot. Amplitude response, sure, has local maximas on the angles of zeros, adding 0 at unit circle results in attenuation of signals on that angle, on that frequency. Likewise, if you take the pole, put it next near to the unit circle, you will get a local gain on that frequency. Phase response, it's related to the time difference. Well, as you think of it as if you have sine coming in on a system, then you have the amplitude response times the sine of omega t plus phase difference. So you can see that actually this phase difference can be represented also as the derivative of this one times t. Okay. Group delay, which is the frequency derivative of phase response, that gives you the how many time steps or how many seconds this each frequency component will delay in the system. And here we have three different kind of systems: linear, nonlinear, zero phase. And that was the picture of that one. Okay, good. Any questions?
I had a question.
Yep.
You said that a transfer function and impulse unit impulse is the same. So
Yes.
transfer function is a Z transform of unit
Impulse response.
impulse response.
Yes.
Okay. Yes. Yes.
It was somewhere here. Here. Yes. So this is the Z transform of, well, it's Z transform, Z transform impulse response. So this is practically a also one way of defining the transfer function. In some of the DSP books, it actually takes this as a definition, but on the other hand, well, definition of H of Z is that whatever you have this Z transform of output is the same as transfer function times Z transform on input. So it's the frequency space representation of the system. Alrighty. Other questions? Would you like to explain why we do use group delay? Okay, yes. Yes. Hey, let me try something new. Let's see how does it work. Group delay. Let's take that group delay here. Do I have any graphs of group delay? No, I don't have any graphs of group delay. I should actually have it here, but anyways, let me turn on my camera. I have a really good tablet now, although my pen is a little bit too narrow file, but that one. But anyways, typically a group delay, it looks more or less something like this. So we have a passband of the system somewhere in here. This is the frequency. And actually the group delay is time, how long the signal actually delays on the system. So if we have one signal here, F1, another here, F2, and we have a system which basically have these two components, F1, how do I mark it? Okay, we have two sinusoids, F1 and F2 coming in, carrying parts of the same information. So at the start we have maybe like that. So this is the F1, F2 on one side of the system. There on the other side of the system, the first one has a time delay of a small one, but the other part actually has a time delay of, so we have two different time delays, delta 1 and delta 2. This is delta 1, this one is delta 2. So coming out, this signal filtered actually would start here, and the other signal starts here. That's not coherent data package anymore. So that's where the this group delay is actually pretty important parameter, especially when you are designing systems for the data transmission. So you can actually on the, if you have a totally digital transmission, then you will design a system which is totally linear, the phase response system, meaning flat, constant time delay, constant group delay. Okay, but you also know that in different media, these frequencies can actually travel different speed. For example, audio from long distance. Audio signal goes in, for example, in air roughly at 320 meters per second or something like that. It's roughly because it actually has this wavelength dispersion, meaning different parts of the audio signal will have different time of flight. Okay, if you are then want to reconstruct that signal, you need to take into account this non-constant the group delay. So basically, then you can design this group delay to compensate this wavelength dispersion. So two frequencies always have different delay. No, if you have a system with the constant group delay, so it's basically zero phase, not zero, linear phase response. Linear phase response. Then you have the time delay always decay. Remember, the phase, this group delay is actually the the frequency derivative of of the phase response, and here we have the phase response was k times omega for linear phase, and that's simply k. So practically a linear phase response system have a constant time shift. So for constant time shift, it would mean for the same signals, k and k. So they would actually be still in a coherent package, same time package. Got it? Okay, great. Excellent questions. So let's have a break and come back online in say at no, it's 12:08. So let's come back online 12:25. Okay, and 12:25, I will start with this exercise. Exercise 3.